Welcome back to another episode of Science with Surback. Today what we're going to be talking about is the solution process. And before we get going into the video, I just want to outline a few objectives. So objective number 1, describe the energy changes that occur in the solution process in terms of the solute, the solvent, and the solute-solvent attractive forces. Objective number 2, recognize when entropy is increasing or decreasing when a solute is dissolved in a solvent. Objective number 3, rationalize the solubilities of substances in various solvents in terms of their molecular structures and intermolecular forces. Objective number 4, describe the effects of pressure and temperature on solubilities. And objective number 5, state and use Henry's law. So we get a little bit background here on the first couple of pages of notes here on what solutions are. So simply put, solutions are defined as homogeneous mixtures of a solute and solvent. Now, just because something is a homogeneous mixture doesn't mean that it can be a solid, liquid, or gas. So remember, a homogeneous mixture can actually be a solid, liquid, or gas. Now, it's also important to remember that solutions form when one substance is dispersed uniformly throughout another. Now, there's also some factors that affect the solution process. One of these factors is that there are natural tendencies of a substances to mix and spread into larger volumes when not restrained. And then the other factor here is that intermolecular attractions are often involved in a solution. So what that means here is that interactions between two different molecules in that solution are going to interact with one another. Now, as we go through this, one of the easiest ways to think about the solution process is really through a process of actually making a solution. So we transition here to mixing a substance or mixing substances together. And one example that comes to mind, it's very easy to see here, is the interaction between solid salt and water. So in this example here, again, a very simple example, but what I have in front here, I'm going to move this set of notes, but what I have here is just a beaker, and I'm going to put some salt in that beaker. And as you can see, we have the solid salt, and I'll put a little bit more in there. And then I'm just going to come in and I'm going to add some water. Now, what happens here, we can all see this, we've all done this, but what happens here is that eventually we'll mix this together and we'll get this nice clear solution of salt water. Now, it will look pretty clear and colorless, but obviously if you've ever tasted salt water, it does have that unique salty taste. So it may seem like, what's the big deal? But there's actually a lot of things happening as we go through this, as we mix this particular solution. So I'll get this cleaned up here and we'll get back to notes to talk about, hey, what is the chemistry behind what happened here? All right, so what is happening? A lot's happening. We're going to go through and we're going to draw a picture here about what just happened. So in our beaker here, we initially had NaCl. Okay, so NaCl, I'm just going to draw it as the chemical formula of NaCl. That's our salt. And then what we did here is we added water. So we poured water, and I'm just going to draw this by adding an arrow. And so we added water into that beaker that contained the salt. And so what happened as a result of this is as follows. we had the water, which I can bring my solution of salt water and show you again. We had the water dissolve the salt, and you can see here it's starting to get a little bit more clear. It's starting to become that clear and colorless solution. And so what's happening here is this. These salt ions, or the sodium and chloride, break into their individual ions, and that's because they are surrounded by that polar water molecule. So in the case of the sodium, it gets surrounded by our oxygen, which has a partial negative charge, and our chloride, our Cl here, gets surrounded by the H's, which have a partial positive charge. So I'm going to draw a couple of H's around our Cl. And so what is happening here is this. We have an interaction between the water molecules and the ions, the sodium ions and the chloride ions, to produce this solution. Now there's some other things that I want to talk about here, and that is the terms we initiated or went over a little bit on the other page, but that is the concept of the solute and the solvent. So right here in our case here, sodium chloride, this right here is our solute. And the solute is defined as a substance dissolved in a solvent to form a solution. And I forgot one key word here, and that is the solute is defined as the substance dissolved in the solvent to form that solution. So our water in this case, I'm going to draw an arrow here. Our water in this case is then going to be our solvent. And now our solvent is defined as the dissolving medium of a solution. And now a really key thing to keep in mind is this. The solute is normally the component of a solution present in the smaller amount. This means here that the solvent is normally the component of a solution present in the greater amount. Now, the last point I want to make here with this particular section of notes here is that mixing of substances occurs spontaneously unless molecules are restrained by sufficiently strong intermolecular forces or barriers. And I know I'm running out of room here, but I'm going to squeeze this in just below where I had my beakers. Again, I squeeze that in here, but it says mixing of substances occurs spontaneously unless molecules are restrained by sufficiently strong intermolecular forces or barriers. Okay, so now that we have an idea of how the solution process works in terms of the chemistry behind it, now we can shift gears to, okay, what specifically is happening? We talked about intermolecular forces in this set of notes, but we really haven't talked about what intermolecular forces are. So we get into the details here with the next section of notes. And so the intermolecular forces occur in three different types of attraction when we have this solution formation. The first of these three types is a solute-solute interaction. And these things occur between solute particles. So in our example that we went over, the solute-solute interaction would be occurring between those sodium chloride units, or those sodium chloride particles. Now, there must be overcome, or this type of interaction must be overcome in order to disperse the particles throughout the solvent. Now, the second type of interaction involved in a solution is a solvent-solvent interaction. And now these occur just between these solvent particles. Now, these solvent-solvent interactions also must be overcome to make room for the solute particles in the solvent. Now, in our example that we did, the solvent-solvent interaction would be the interaction of those polar water molecules interacting with the other polar water molecules. Now, the third type of interaction is the solvent-solute interactions. Now, this type of interaction is going to occur as the particles mix. So in our example that we've been using here, that sodium chloride dissolving in water, the interaction where the water molecules actually surround each of the ions, the sodium and the chloride ions, that is that solvent-solute interactions. Now, some other term, or another term to keep in mind, is what we have known as solvation. And solvation is defined as the clustering of solvent molecules around a solute particle. So in our example here, it's actually that second picture I drew where the water molecules are completely surrounding each of the sodium and chloride ions. That is that process of actually having the solvation occur. Now, these things here, if solvation occurs with water, it's referred to as hydration. All right, so now let's talk about another piece that is occurring as we have a solution occurring. So we have these interacting or mixing of these types of forces. And then what we also have to be concerned about here in chemistry is the energy that is required to produce a solution. So the first thing to remember here is that the formation of a solution requires 3 steps that involve energy. So the first step that involves energy is the separation of the solute molecules. And I know we haven't talked about a whole lot of thermodynamics or thermochemistry, but this delta H stands for change in what we call enthalpy, and we can think of that as heat for the time being. Now, the other step that involves this energy is the separation of solvent molecules. So again, the delta H just stands for change of enthalpy, which we can think of as change of heat, specifically for that solvent. And then the third step that involves energy is the formation of the solute-solvent interaction. And so that is the change of enthalpy, or you can think of it as heat, of the entire mixture. Now, this does have a formula to go along with this process. And that formula is the change of enthalpy of the solution is equal to the change of enthalpy for the solute plus the change of enthalpy for the solvent plus the change of enthalpy for the mixture. So it is going through and it is adding all of the changes in heat involved in the solution formation process. Now, there's another thing too that's really important for us to think about, and something that in the lab we can actually feel and experience as we produce a solution, and that is the sign of what delta H of the solution is. So the first sign that we'll talk about is that if delta H is positive, what this means is the solution process is endothermic. And so the important thing here with a positive delta H is that to form this solution, it's going to require heat. So heat either from the outside environment or something like a hot plate would also be considered an outside environment, is going to have to be added for that solution to occur. On the flip side, a negative delta H means that the solution process is exothermic. And so what that means for us is that it gives off heat. So when we have an exothermic reaction or an exothermic solution formation, you'll actually feel the heat, or the container, the beaker, whatever that solution is being formed in, getting warmer. Now, there's an additional topic here that we need to think about of this delta H of that solution. And that is if we can determine if a solution will form just by using these delta H's, or the changes of enthalpy of a solution. Now, these are general statements that I'm about ready to give here, but solutions form if the delta H of the solution is negative. Almost always that if we have delta H of a solution that's negative, they are going to form. Now, on the flip side here, if the delta H of the solution is too endothermic or requires too much heat, the solution is not going to form. So again, there's a fine line here of, hey, this solution requires too much heat, and because of that, it's not going to form. Again, these are general statements here, and I know we haven't gone over a whole lot of thermochemistry, but that gets you a broad overview of that heat requirement, or the energy, if you want to think of heat as energy, because it is. What is the energy requirement to produce a solution? All right, so now let's get into the business of solutions and chemical reactions. So what we have here with solutions and chemical reactions is just an example. And so our first example is solid nickel being dissolved into hydrochloric acid to produce nickel 2 chloride and hydrogen gas. So I'm going to pause and write that chemical equation down. All right, so there's that equation that I just talked about. Now, what happens here is this, and I'm gonna draw another arrow to nickel 2 chloride. This nickel 2 chloride is a solution of nickel 2 chloride. Now, what happens here is that this solution of nickel 2 chloride formed from a chemical reaction. So I'm going to write that down here. Now, in my other example here is when salt interacts with water and we form that salt water solution. So what happens here is that the solid salt, sodium chloride, goes through and dissolves with water, except we have a unique thing that happens here. All right, so what happens here is this. What happens here is we get a solution of sodium chloride, and we went over this in the picture where the sodium ions were surrounded by water and the chloride ions were surrounded by water. But notice here there is no chemical reaction used to form this solution. So I'm going to pause and write that down. So what happened here is this. We did not have a chemical reaction, and that's because substances didn't swap places, they didn't trade partners or go through a chemical reactions. We had a reaction, or excuse me, we had a solution formed by physical processes. So the bottom line up front here is that you can have a solution form from either physical or chemical processes. So again, I want to make this point real clear here, and this is a general statement for this entire page, is that you can have a solution form by either a chemical or a physical process. All right, so now what we'll talk about here is just some terms to be associated with, familiar with, as we move on in the unit with solutions here. So we get to our first term, and this first term that we need to be familiar with is crystallization. Now, crystallization is defined as the process in which molecules, ions, or atoms come together to form a crystalline solid. And so this process is the opposite of dissolution or a solution forming. Now, we can tie together a chemical equation used to represent this process of going from crystallization to solution as follows. So what this chemical equation is this. You have the solute and the solvent interacting. And we're just going to call that over here on what we traditionally know as the reactant side. Now, what happens here is that this forms the solution, okay? And I put an odd symbol here, and this is known as equilibrium. So what's happening here is as the solute and solvents interact, they form the solution. Now what you can't see here, and especially this salt water mixture that we've gone through, is that the solution process continues. So sometimes the sodium or chloride falls out of that solution, and then before you know it here, it gets reabsorbed because we have enough water to interact with this particular solution and form the solution again. If however, we took out some of the water, we would have the solution go back in its individual parts. Now, if we heated up the water would go into the atmosphere, and that solute would be that solid crystal structure of salt. So we've all heated salt water, and we've heated it to oblivion there. And what happens here, you evaporate that water, what's left behind is that salt crystal, and that's really the process of crystallization. It's taking whatever we had in solution in terms of the solute particle and putting it back into the individual solute, not involved in that solution at all. All right, so now there's just a couple more terms that we need to go over, and we'll switch gears here to what we have known as kind of the types of solutions. So we start out here with our saturated solution. Now, a saturated solution is just defined as a solution in which undissolved solute and dissolved solute are at equilibrium. Now, to put it simply here, this is going to occur when there is no further increase in the amount of dissolved solute. So in a saturated solution, if we added just a little bit more of a solute, it couldn't get dissolved. It would just drop to the bottom because there's not enough solvent to surround that particular solute particle. Now, on the other hand, an unsaturated solution is defined as a solution with a concentration of dissolved solute that is less than the solubility. Now, I'm going to leave the term solubility alone for a second because we're going to come back to it on the next page of notes. So this brings us down to our final term, and that is a supersaturated solution. Now, a supersaturated solution is defined as a solution with more solute dissolved than in a saturated solution. Now, you may be thinking, hey, just above you said a saturated solution contains the maximum amount of solute that can be dissolved by a particular amount of solvent. And that's true, but in a supersaturated solution, what happens is this. Typically, a solution gets heated up, and when you heat something up, as we'll see here in a few moments, as you heat something up, it can dissolve more and more of that solute. Now, some substances, as you cool them down, what happens is because you heated them up and you slowly cooled them down, it allows more of those solute particles to be dissolved, and thus, when you think about it here, it's going to contain more solute particles than that given amount of solvent should. But it's all based on that physical process of heating it up and then slowly cooling that solution down that contains more solute than it should. So let's get back to that term I mentioned earlier with solubility. Now, solubility is just defined as the amount of solute required to form a saturated solution. And our solubility can be affected by 4 factors. The first factors that affect solubility is the nature of the solute. In other words, what is the solute? The second factor is the nature of the solvent. And again, we can think of, well, what is the solvent here? The third thing that affects solubility is the temperature. And then the fourth factor that affects solubility is the pressure. And now this is isolated for gases. All right, so let's go ahead, let's talk about each of these 4 factors in a little bit more detail in the next couple of pages of notes. So we get here, and the first thing here, we have solute-solvent interactions. And so what this is, or what this set of notes talks about here, is actually the first 2 factors that we listed in our list above. So the thing we have to remember with solute-solvent interactions is that in general, the stronger the attraction is between the solute and solvent molecules, the greater the solubility. Now, this statement can be added to by saying likes dissolve likes. So what I mean by this statement of likes dissolve likes is that things like polar molecules can dissolve ions, polar molecules can dissolve other polar molecules, and nonpolar molecules dissolve other nonpolar molecules. So again, with this statement here of likes dissolve likes, it really emphasizes or makes a very important note here that we have to be aware of those solute particles and what they consist of. All right, so let's talk about a few more terms here, a few more things from that list, and going through this process here. So if we get into the solution process where we're mixing 2 liquids together, we can come across 2 different terms that may describe how these liquids interact or don't interact. And so we have miscible liquids here, which are defined as pairs of liquids that mix in any proportion. So a good example of a miscible liquid, or a set of miscible liquids, would be water mixing with an alcohol. Another term that could be used to describe if 2 liquids interact together and don't mix are immiscible liquids, which are just defined as pairs of liquids that do not mix significantly. So a good example of immiscible liquids would be oil and water trying to mix. These 2 things don't mix, and the oil will sit on top of the water. All right, so now we need to shift gears and talk about that third factor, which was pressure and solubility. So solubility of a gas, or the solubility of a gas in a liquid, is a function of the partial pressure of the gas over the solution. And the solubility of a gas in a solution can be summed up by Henry's law, which states that the solubility of a gas in a liquid solvent is directly proportional to the partial pressure of the gas above the solution. Now, Henry's law can be summed up in the following formula. And so the formula here is that the solubility of the gas is equal to this Henry's law constant we call K times the pressure of the gas. And that little g just stands for gas. So again, the solubility of the gas is labeled as S little g. The K is the Henry's gas law constant. And the pressure of the gas is just the partial pressure of a particular gas. So let's put this knowledge to the test here. If we have a soft drink, a carbonated beverage, also known as a soda, is bottled with a partial pressure of 4 atmospheres of CO2, what is the solubility of the gas if we know that K is 3.4 times 10 to the second moles per liter atoms? So what we do here, again, always list out what we have for a formula. So we have the solubility equals the Henry's gas law constant times the partial pressure. So in this case here, it does not talk about the solubility, so that's what we're going to be finding, is equal to our K, which is going to be given here because that's a constant. I don't expect you to know that here. It would be 3.4 times 10 to the second moles liter atmospheres multiplied by that partial pressure. Well, the partial pressure of the gas, in this case carbon dioxide, is 4 atmospheres. So we have 4 atm. So all we're going to do now is calculate this problem out. So remember in your calculators that when we're using scientific notation, make sure you put it in parentheses there. Okay. So what I'm going to do here is this. I'm going to put in parentheses. I'm going to put 3.4 times 10 to the second. I'm going to close the parentheses, and then I'm going to take that number and multiply it by 4. So the solubility of the gas is 1,360, and when you would round that to significant digits, okay? So what pops out in your calculator is 1,360 moles per liter. But if you would round this to the correct number of significant digits, the solubility of the gas would be 1,400 moles of CO2 per liter. And so that would be your ultimate rounded answer there. All right, so we have one more thing to talk about here with our general orientation of gases, and that is the effect that temperature has on solubility. So we'll shift gears here and we'll move to what effect does temperature have on solubility. So we break these into 2 different categories, and the first category that we break it down into is with solids. So we'll start out here with our solids. Now, solids have this. The general solubility, or generally solubility, of most solid solutes in water increases as the solution temperature increases. And so a great example of this is adding sugar to tea. The hotter that solution of tea gets, the more sugar you can add. Now, the other category here that we have to talk about is with our gases. So the gases, generally the solubility of gases in water decreases with increasing temperature. And a great example of this is a soda going flat in hot temperatures or warm weather. So in this case here, the hotter the soda gets, the less carbonation or less CO2 is dissolved in that particular soda. All right, so this has been quite a jam-packed section of notes here. It really introduced you to a lot of the big concepts of the solutions. And so what I want you to have in the mindset here is, as we go through this solutions unit, keep in mind that all these little things with the interactions of molecules and particles are occurring to give us this big picture of what is happening as a solution is involved in either a chemical reaction or it's involved in another process. Now, the other thing to keep in mind is we haven't really got into the details of atoms and molecules and intermolecular forces, so I don't expect you to be an expert at what we just went over. Again, I just want you to keep that in mind as we go through this entire unit. There's a lot occurring just to produce that solution of salt water, or just to produce any type of solution. There's a lot of chemistry involved in what is happening during that process. Well, I hope you have enjoyed, and as always, subscribe.